In this video, we're going to talk about buffer action, and we're going to just demonstrate an example of how a buffer works. So let's say, for example, you begin with, you have water. You have this beaker of water, and if it's pure water, then if you measure the pH of that water, the pH ends up being is 7.0. Okay, and if you decide to add, let's say you add 0.020 moles of HCl, okay, to this water, so that goes into the water. Well, the result is actually a pH of 1.7. And how does that come about? Well, all you got to do is take the negative log of the 0.020, which is the concentration in moles per liter. So we're going to assume that the volume of that solution is equal to 1 liter, to make things simple. And therefore, if you take the negative log of that quantity, it ends up with a pH of 1.7. So therefore, the net pH change is equal to 7.0 minus 1.7, which gives you 5.3. That's the pH change. I'm going to call that delta pH, okay? I'm going to keep that there. Okay, and then on the other hand, if we decide to add, instead of 0.020 moles of HCl, we add 0.020 moles of sodium hydroxide, which is a base. Okay, and when we add that, again, you take the negative log of the hydroxide ion concentration, just like we did for the HCl, which was an acid, and that ends up giving us a pOH of 1.7. And notice very carefully though, because we took a base, we can't directly determine the H plus ion concentration. We have to do it by finding the pOH first, which is the negative log of the OH minus ion concentration, which directly comes from the OH minus ions in NaOH. And then from there, we can kind of back into the pH by using the relationship pH plus pOH is equal to 14. And so if you plug 1.7 out here, then pH comes out to be 14 minus 1.7, which is 12.3. So therefore, the net change, again, the net change of the pH when you add sodium hydroxide, which is a strong base, to water, will be 12.3 minus 7.0, which was the pH of water, which ends up being 5.3. Okay, so as you can see, whether you add a strong acid or a strong base, the pH jumps significantly. Okay, and I'm just gonna box this for reference. That's the change in pH for base, and then the change in pH for an acid is up here. Okay, so now if you take a buffer, so that was the case where you didn't have a buffer. Okay, so now if you take a buffer, and a common buffer solution would be acetic acid. So CH3COOH, that's a weak acid. So buffers are always made with either a weak acid and its conjugate base, or a weak base and its conjugate acid. Okay, so you take a weak acid and you add its conjugate base, which is basically the acid without the H plus ion, and that's the conjugate base. The name of this acid is acetic acid, and the name of the conjugate base is the acetate ion. Now, because usually you cannot get the ion in the form of an ion, usually the way to get that is by taking the salt of the iron. So you take the iron with a sodium with a positive sodium ion to kind of balance the charges out, and the name of this would be sodium acetate. Okay, so if you take a 50-50%, or basically a 1:1 ratio of both the acid, the weak acid, and the conjugate base, you end up getting a buffer. Okay, so let's say we have a solution of buffer. If you take, just to kind of try to visualize this quantitatively, if you take a 0.50 molar solution of acetic acid and you mix it with 0.50 molar solution of the acetate ion, so basically that's your acid, that's your conjugate base, excuse me, and you measure the pH of the solution. To measure the pH ends up being 4.74. okay, if you add, now at this point in time, if you add the same 0.020 moles of HCl, which is your strong acid, to that solution, okay, the new pH of the solution is excuse me, is only 4.70, so it barely changes. And then if you add a strong base, so we'll take the same 0.020 moles of NaOH, which is a strong base, the new pH of the solution ends up being 4.77. Again, barely changes. Okay, and if you go back up and take a look, notice carefully, the pH changed when you added the acid to just pure water was 5.3, and out here when you added the acid it was 4.7. so the net change, here's a different color out here, the net change, so the change in pH out here was 4.74 minus 4.70, which is 0.04. See, barely changed. And then if you check the pH change for the base out here, that is what, 4.74 minus 4.77, or we just take the absolute of that because we're just concerned with the change and not the sign. That's 0.03. So either way you look at it, the pH barely changes, and that's the power of a buffer. So let's try to understand why the pH barely changes when you have a buffer as opposed to when you don't have a buffer. So if you take a look at the same system out here, you have, CH3COH, that's the acid. You react that with water, so you're making that solution, and then there's an equilibrium that sets in. But on the other side you have the conjugate base, and then you have H3O plus, which is the conjugate acid. So now if you add acid to this, okay, when you're adding HCl to this, so that's the strong acid, what ends up happening is the strong acid, it tends to react with the negative charge because acids produce H plus ions. So that H plus ion combines with the negative charge, and that pushes the equilibrium in this direction to form CH3COOH. Okay, so think about it as in terms of Le Chatelier's principle, or you might have learned this in equilibrium if you recall, Le Chatelier's principle. So basically what happens is the hydrogen plus ions basically combines with the CH3COO minus and pulls that out from the right hand side to make more product. Okay, so as a result, the equilibrium shifts to compensate. So what's going to happen is the CH3COO minus basically reacts with the H plus. So you're adding more acid, it basically forms more H3O plus. The CH3CO minus, which is present out there, tries to neutralize that effect by capturing more H3, capturing some of the H plus to push the equilibrium back to the left to neutralize the effect of the added H plus ion. Now, if you do the same thing with base, okay, so I'm going to just rewrite that equation out here so you can see what happens when you add a strong base. So you add a strong base to this, so that's really the strong base is the OH minus. So the OH minus, when you add it to this, the OH minus, there are a couple of ways to look at it, but the OH minus is gonna try to react, you can think of it as reacting with this acid out here to produce this and this, okay? As a result, when the addition of the OH minus shifts the equilibrium, kind of disturbs the equilibrium because more this and this is created. But when more of these two are created, they recombine to push the equilibrium back in this direction. So the net effect is basically almost zero. Okay, so that's basically what happens in terms of Le Chatelier's principle. And if you recall, Le Chatelier's principle basically says that when you have the addition of anything to disturb the equilibrium of a certain reaction or a process, then the reaction or process tends to offset that by moving the equilibrium in the opposite direction. So if you add products, in the case of the acids, when you added acid, you added a product out here. So what happens is more reactant is produced to offset the equilibrium. When you add a reactant out here, it's not truly a reactant, but what it does is it kind of captures the hydrogen plus when you add the OH minus out here, which ends up producing CH3CO minus plus H3O plus to offset the effect of the OH minus on this side. So either way, the ratio of the product to the reactants always stays the same, hence maintaining that equilibrium.